from the current slide. Oh, let's turn on the projector. Sorry about that. Now, I think I've been telling you this was coming for a week or two, or I suspected it anyway, but yesterday when I went to put in my attendance, I noticed that they had removed all unpaid students from the rolls, which since I haven't put in your attendance since then, I don't know if that affects anyone who's been coming. I'm saying this mostly for people who are not here. If you are planning to stay with the course and you haven't completed payment and your name is no longer showing up on the roll, please try to get something worked out between the business office, financial aid, somebody, and get back in the class. Now, what they tell me is we're not supposed to let people back in the class until they get that worked out with the financial. I would just as soon you be here as not be here, with this caveat. If you don't pay, there's no way I can give you a grade, okay, because your name's not going to be on the official roll. You can sit in here to your heart's content. It's a free country, but you're not getting a grade unless the college has accepted your money. And at some point, they're not going to accept it. So the excuse of, well, I've been to class all this time, to me, that doesn't hold water. If you haven't paid, yeah, you're welcome to come and sit anywhere you want to, but until you pay, you're not going to get a grade. Okay. So, sorry we had to mention that, but I did notice yesterday unpaid students had been removed from the roll. All right. Now, my computer has been doing really well all day, and now it's phasing in and out, but it seems to be holding steady on power, so hopefully it will. We were in example 5, which is being shown here, and we just ran out of time before we could complete it, so let me see. Nope. Okay. So let's go back to what we had done so far. Here's a function, f of xy is a piecewise defined function. It has one set of values when xy is not equal to 0, 0, and 0 when xy is equal to 0, 0. And that's all it says. It says show that f sub xy, f sub x at 0, 0, and f sub y at 0, 0 both exist, but the f is not differentiable at 0, 0. Okay. I think we have done the first part already, but let's do it again just to review. All right. What is your f sub x at xy? Second? Partial of f with respect to x. Okay, now let's say quotient rule, right? Okay, and how would that go? Okay, it's the low, which is x squared plus y squared, times the sine of high, d high, which is with respect to x now. Partial of the numerator with respect to x. Negative 3y. Okay, very good. Minus high d low, and the high is negative, so that's going to be plus 3xy, and what's d low? 2x. Okay. All over x squared plus y squared squared. Okay? Now, it says show that these both exist, okay? At 0, 0, I don't see that existing. I guess they mean the limit exists. So I'm having trouble with just what it's saying here. It says, show that f sub x at 0, 0 and f sub y at 0, 0 both exist. At 0, 0, that does not exist, okay? And I think if we did f sub y, we get the same thing because you have the same thing in the denominator. And then the solution here says, you can show that f is not differentiable at 0, 0 by showing that it is not continuous at that point. Okay? So I don't know how they can say show that they both exist and then say they're not differentiable. It seems like that's contradicting each other just in the instructions here. So, and this is where I kind of got bogged down before. It just doesn't look like it is possible. They exist everywhere else, but not at 0, 0. Okay? And now what they suggest that you do here is to just talk about f, not f sub x, because if f doesn't exist, is not continuous, then you can't really talk about f sub x, okay? So, and here's the tab. All right. But here's what they talk about here. They're just going to look at f now. Forget about the f sub x. And I haven't even done f sub y because I don't think you can show it exists because it doesn't exist, okay? So anyway, if you look at f sub xy, and this is what they recommend too, if you Matthew, right? Good deal. If you were to approach 0, 0 from several different directions, well, let's start with, let's say, on the y-axis where f of x is equal to 0. If you came in that way, this would be 0 over y squared, okay? And as y is approaching 0, that's getting infinitely large, okay? So that doesn't seem reasonable. If you did approach, at least from the positive side, let's do it that way. From the negative side, it would also be getting very large, okay? You actually be get 0 over 0. Okay, back up a minute. If you're coming in the, say, the positive y-axis, say y-axis, x-axis, where y is equal to 0, then the numerator would be 0, but the denominator would be would be x squared. So it'd be 0 over x squared. So that's 0 all along there, okay, until you get right to 0, and So that limit does exist, okay? And from the minus y-axis, positive and negative x-axis too, y-axis too, that would be okay. I mean, it looks like it might exist, the function might exist. Not saying it does, but the function might, because there's zeros coming in here and here. But if you come in a different way, like y is equal to x, so let's do it as y is equal to x, then this would be minus 3x squared over 2x squared. So that limit, as x is approaching 0, that would be minus 3/2, okay? Because it's just a number minus 3/2. But if you did, this is where y is equal to x. If you let y equal minus x, then what you have then is 3x squared over, and that would still be 2x squared. So at y is equal to minus x, you take the limit as x approaches 0, or as y approaches 0, either one. This would then be 3/2. So hold the horses here, coming in the diagonal line this way, you'd be down there negative 3/2, and coming in from the minus side, it would be a positive 3/2. No way that ever going to be it's not going to be continuous at 0, 0. Nowhere close. Nowhere close will it be. Coming some directions it will be, but not every direction. Okay? Now, so the limit of f of xy as x approaches 0, 0 does not exist. You can conclude it's not continuous at 0, 0. And then by the theorem 13.5, which was just back one slide, that one right there, if it's not continuous, if a function is differentiable, then it is continuous. If it's not continuous, it can't be differentiable. Okay? Now, let's show the picture. Now, I'm not certain that this picture is all that helpful, but let's see it. You can show that f is not differentiable at 0, 0 by showing it is not continuous at that point. So that's why I said, how in the world can their problem say show that these both exist? No, they don't exist, okay? So I thought the problem was very poorly stated, okay? Now here's the deal, and I'm not sure this is very clear at all. To see that f is not continuous at 0, 0, look at the values of f along two different approaches to 0, 0 is shown here. Okay, along the line y is equal to x, that's this one, okay? You're going in here toward negative 3/2. As you come from y is equal to minus x, that's this one, you're going to positive 3/2. I don't know what that little line, oh no, this is underneath, okay? So this is underneath, that's the end of this one. At negative 3/2, here it is at positive 3/2. No, okay? There's no way that can be continuous at 0, 0, okay? So I don't even know how they drew the picture here, because there should be a big gap in there, and they don't show it, okay? And that's basically all they do. Along the line y is equal to x, then you have the limit as x approaches 0, 0. You have negative 3x squared over 2x squared, which is negative 3/2. And along when y is equal to negative x, from negative x to 0, 0, then you are 3 halves, 3x squared over 2x squared, which is 3 halves. So the limit of xy as xy approaches 0, 0 doesn't exist. You can conclude not continuous from that, from our theory. Therefore, it's not differentiable at 0, 0. So why did the problem say show that the partial of f and partial of y both exist? They don't. It just says it's not differentiable. On the other hand, here we go. By the definition of partial derivatives, we have the f sub x at 0, 0 is f at delta x0 minus f at 0, 0 and I don't even see how they got, the formula here is right. How they got that, I don't know. And they say divided by delta x would be the limit of 0, and this would be a limit of 0. Now, what I don't see with this is how they get this. They say f 0, 0 is 0. Whereas just earlier, they said, I'm sorry. That's absolutely right. Remember, the problem stated f of 0, 0 is 0. That's the piecewise defined function. That was that part of it. And this part would then be just as if y is 0 and delta x is not 0, but delta x is approaching 0, then this would be, as long as delta x is not 0, your numerator would be 0 divided by 0, okay? Divided by delta x. So yeah, okay, now I see what they're talking about. Because this thing right here was defined to be 0. Not what you calculate to be 0, but defined to be 0. And this one approaches 0 as delta x is going to 0. Now, the reason for that, and I'm not sure this is copacetic either. Well, no, that's what I said earlier. Let's see, where is it? Yeah. Here's your function. And as if your y is 0 and you're letting the delta x approach 0, then that appears to be going towards 0. Because you have the 0 up here and you have a delta x down here. So that appears to be going to 0. And then on the other hand, as delta y is approaching 0, this, if x is 0, that's also 0. And then this would be, yeah. So I guess by their limit values here, wait, not there, these, then it looks like the functions do exist, f sub x and f sub y, mostly because it's as you're approaching 0, however you're getting there, you're approaching it on close to horizontal lines, however you're getting there. The trouble is the horizontal lines don't meet, okay? They're horizontal, so the derivatives are the same, but that doesn't mean the lines are the same. So I guess that's what they're getting at. Sort of an esoteric point, totally. So the partial derivatives do exist, the partials are the same, but the lines that they're partial to are not the same. Okay, I guess that's what it's getting at. So that ends 13.4. Homework exercises here. Do any of the odds 3 through 7, they're all at Calc Chat, 3's at Calc View. Do any of the odds 9 through 13, they're all at Calc Chat, 11's at Calc View. Do either 15 or 17, they're both at Calc Chat. 19 should be at Calc Chat. You can explore doing that. You don't have to if you don't want to, but see how that looks at Calc Chat. Then you can do any of the odds. Goodness gracious, they got a lot of them. And I think I told you this before, any of the odds 21 through 33. Now there's a lot of different problems there. There's area problems, volume problems, numerical analysis problems, wind chill problems, power problems, and inductance problems. So you got a lot to choose from to do the ones that seem closest to whatever major you are and where you're heading with it. Then do either 35 or 37. They're both a Calc Chat. 35 is a Calc View, and 39, or do number 39, is both Calc Chat and Calc View. Very similar to the one we just did. All right, now we're ready for 13.5. That was just the last little bit we had in 13.4. Let's go to 13.5. This is one long chapter, folks. There it is. Okay. And let's go from current slide. All right. Chapter 13 again still is functions of several variables. 13.5 is chain rules for functions of several variables. Okay? Now, objectives here are to use a chain rule for functions of several variables, which is the title of the section, and we'll find partial derivatives implicitly, just like we did derivatives implicitly back a couple courses ago. So here's your theorem 13.6, the chain rule when you have one independent variable. Okay? Shoot, that's what we have had in the past. Okay? Sort of, but not quite. So here's W. It's a function of two variables, x and y. At first glance, you'd say, well, those are two independent variables. Well, not quite. Where f is a differentiable function of x and y, like we said, but x is not completely independent because x depends on t. X is equal to g of t, and y is equal to h of t. So your ultimate independent variable is t. X and y both depend on t in different ways, and then your w depends on the x's and y, which both depends on t. So g and t are both, g and h both have to be differentiable functions of t. Then w is a differentiable function of t as well. Okay? And here's how you do that. Keys get all messed up. There we go. All right. Since w is a function ultimately of t alone, then this can be an exact derivative, dw dt. But dw is not a function of one variable in terms of x and y, it's two. So that's going to be the partial of w with respect to x times the derivative of w x with respect to t, because x is a function of t, plus the partial of w with respect to y times the derivative of y with respect to t. So this is if you have only one independent variable, what I call two intermediate variables, x and y. They're not completely independent. They're independent of each other, but not completely independent. And then one dependent variable, w. So this is sort of how they show it with a diagram. And I'm not sure the diagram really helps me that much, but I guess it's okay. Ultimately, you only have one independent variable, t. So your dx dt and dy dt are normal derivatives. But x and y are both variables that w depend on. So then when you do the derivative of w with respect to either of those, you have to use the partial derivatives because of two variables down here. So partial of w with respect to x, partial of w with respect to t. I mean with y. But then to get from w to t, you do partial of w with respect to x dx dt plus the partial of w with respect to y dy dt. That's exactly what you got there. That's the chain rule when you have one independent variable, one dependent variable, and two what I call intermediate variables. Okay? Now, let's do one. Let w equal x squared y minus y squared, where w is equal to sine t and y is equal to e to the t. Okay? Find dw dt when t is equal to 0. Well, let's set out to do that. Okay? dw dt, what did we just say? What is dw dt? The partial of w with respect to x, that's first, so what would that be? Well, I'll write it down. Partial of w with respect to x, and you have to follow that with dx dt. The reason that's the exact derivative is x depends on t alone. Okay? But that's just part of the dw dt. The other part is partial of w with respect to y times dy dt. And that's an exact derivative because y is a function only of x, only of t. Okay? So, we need to calculate first what the partial of w with respect to x is. So what's the partial of w with respect to x? You tell me. Has it been? Okay, say that one more time. The partial of w here with respect to x. 2x y. Perfect. Because this one you treat it as a constant and it's not there. The derivative is 0. Now do the partial of w with respect to y. What would that be? X squared. And derivative with respect to y. Minus 2y. Perfect. Okay? Now, what we also need is dx dt. And what's that? Cosine t. You're absolutely right. Let me get these lines out of the way. Okay. Cosine t. And what's dy dt? Derivative of e to t is? E to the t, my favorite of all times. It's so easy. Okay? So now let's plug and chug. dw dt is equal to the partial of w with respect to x, which is 2xy times dx dt, which is cosine t, plus partial of w with respect to y is x squared minus 2y times dy dt, which is e to the t. Now that is, in some senses, a correct answer. However, this is asking for basically a function of w with respect to t, not with respect to x and y. So what we do to get rid of the x and y is plug in what they are. Okay? So this would be 2 times x, which is sine t, times y, which is e to the t, times cosine t. That came from here. Plus, your x squared is sine squared t, minus 2y, which is e to the t. why my pen's not running properly, times e to the t. Now, there's a little bit you can do to make it look prettier. I would write the e to the t after the 2e to the t sine t cosine t. And I think I'd lead off with the e to the t here times sine squared t minus 2 e to the t. Now that may not be the simplest way to write it, but that's, they said evaluate this when t is equal to 0. So the derivative of w with respect to t at t equals 0 would be what? 2 is 2, e to the 0 is 1, but sine of 0 is 0, so this term disappears. Plus e to the 0 is 1 times sine squared of 0. Sine of 0 is 0, and sine squared of 0 is 0. And then you have a minus, probably should put the minus in here, minus 2. So this should be a minus 2. Yep, and that's what they got. I thought they got a 2. Okay, so that is a minus 2. All right. The chain rule presented in this section provides alternatives techniques for solving many problems in single variable calculus. For instance, in example 1, you could have used single variable exception techniques to find dw dt by first writing it as this. If you had plugged in, now what I'm going to do now is just erase some things just because we don't need them anymore, and they sort of are just clogging up the picture here. So there's usually more than one way to skin cats if you don't like cats. So, okay. If you wanted to get dw dt, which is what we were looking for, you could have plugged in what these are here. You said w is equal to sine squared t e to the t minus, that's right, minus e to the 2t. Okay? And then you could have proceeded to do dw dt that way, leaving out the x's and the y's and the x squareds and y squareds, and leaving out all that. You could do that. Now that would be a product rule with a chain rule involved in the first term, and just a chain rule involved in the second term. But then you still have to get it down to a final answer. But you could have done it that way, and it would have been perfectly correct. Okay? All right. They go on and differentiate, so let's us do it too. Goodness, this pen gets to be a pain in the butt. Okay, so let's take the derivative of this. dw dt when it's equal to sine squared t e to the t minus e to the 2t. Okay? The derivative of this involves the product rule. So how does that go? Yeah, of sine squared t e to the t. It's what? Product rule. Second? What is it? It is, here's your w. I'm going to write it up here so maybe it's easier to see. W is equal to sine squared t e to the t minus e to the 2t. You just plug these values in for x and y. Okay? So what's dw dt? Okay, I can't hear. Let me. Okay. Okay. You're probably okay. Be careful, though, when you're doing this. If you're taking the derivative of the first term, I like to start with the outer function. You don't have to, but I sort of like that. That's 2 times the sine. Goodness gracious, this is a pain in the neck. Sine of t, then times the derivative of sine of t, which is cosine t. And all that is times et, because that's your second function. Okay? The product rules is the derivative of the first times the second. Okay? Plus what? Well, you just did the first times, no, I'm sorry, you did the derivative of the first times the second. Now you're doing the derivative of the second times the first. So that'd be sine squared t times e to the t. Okay, that's the first one. And the derivative of the second one is then minus two e to the 2t. All right. Now, if you'll notice, that is what we have down here. 2e to the t, sine t, cosine t, and then down here we factored out e to the t and wound up with sine squared t minus 2e to the t, whereas up there it's e to the 2t. Now if you want to evaluate this at t is equal to 0, then again, this one gives you 0, this one gives you 0, and this gives you minus 2. Worked out a little differently from the bottom, but you get the same answer. Okay? Now, let me clear my scratch, and let's see how they did it. By the chain rule for one independent variable, man, I'm running out of energy so fast. Okay. dw dt, because there's one dependent variable and one and only one independent variable, t, so this is a pure derivative. But it depends on the partial of w with respect to x times dx dt, because that's a pure derivative there too, plus the partial of w with respect to y times dy dt. Okay? Now we take this, take the partials, take the derivatives, plug them in. Okay? And the partial of the first is 2xy times y, times dx dt, which is cosine t, plus derivative of that with respect to y is x squared minus 2y, just like you did, times your dy dt, which is e to the t. Now, that is an answer. It's a correct answer. The trouble is it's not in terms of just w and t. It's in terms of x, y, and t. So to get this in terms of t alone, plug in what x and y are, and that gives you 2 sine t e to the t cosine t plus 2 sine squared t plus 2 e to the t. Okay. Goodness gracious. rewriting this slightly. I just like they must too, to have the e to the t's with the constant. So 2e to the t sine t cosine t plus, and then now they distribute the e to the t across, e to the t sine squared t minus 2e to the 2t. Now that's how the other one's going to wind up looking. So it's fine to get them looking like this. Okay, when t is equal to 0, all you do is plug in. Okay, and of course sine of 0 would be 0, so this term goes away. Sine of 0 is 0, that term goes away. And when t is equal to 0, e to the 0 is 1, minus 2 times 1. Minus 2. All right. Now, like I just said, it can provide alternate techniques for solving many problems in single variable calculus. For instance, in this example, you could have used single variable techniques to find the w dt by first writing w as a function of t alone. Since we're told that x was sine t, so this is sine squared t times y, which is e to the t, minus y squared, which is e to the 2t, minus that. And then when you plug in, this is e to the t sine squared t minus e to the 2t. Then by differentiating w with respect to t, this is your product rule here again. This is what we just finished doing. So what they did was the first times the root of the second, which is e to the t times 2 sine t times cosine t. And then the derivative of this would be minus 2 e to the 2t. And that's what, oh, wait. Sorry. I did the first one here. I didn't do the second. So 2 sine t cosine t e to the t. So we got that one. And this is, the second one of those is times the derivative of this one times that. So that's e to the t times sine squared t. Got it. And then this one derivative is 2 e to the 2t. Okay? And then if you were to plug that in, you get the same result. So the chain rule in theorem 13.6 can be extended to any number of variables. For example, for each x of I, that was your x, y, z type things we had before, is different. If that is a differentiable function of a single variable t, then for w is equal to some function of x1, x2, x3, all the way up to xn, however many you got. 2, 7, 3, 15, whatever. Then and these are all functions of a single variable t. Then the w dt, because w depends ultimately on t alone, so that's a pure derivative, the w dt is equal to partial of w or f, whichever you want to call it, with respect to x1 times dx1 dt, because each of these is a differentiable function of a single variable t, plus the partial of w or f with respect to x2 times dx2 dt, plus dot, all the way up to partial of alpha w with respect to n times dn dt. dx of n times dx of n dt. Okay. Goodness gracious. I know I'm going to make it, but it sure doesn't feel like it. Okay. Now, that was if you had one independent variable. What if you have two or more independent variables? How does the chain rule work then? So we'll keep it down to two. That w is a function of two intermediate variables, f of x and y. But f is, and where f is a differentiable function of x and y. But your x now is a function of both s and t, not just t, but s and t, and y is a function of s and t. They call x the g function and y the h function. I think just like before. Such that the first partials the partial of x with respect to s, the partial of x with respect to t, partial of y with respect to s, and y with respect to t, all exist, and then some partial of w with respect to s and partial of w with respect to t also exist, and here's how it's done. The partial, now it has to be a partial with respect to s, because there are two independent variables. So now to do a derivative of w, it has to be a partial derivative, first with respect to x, later with respect to t. So the partial of w with respect to s will be the partial of w with respect to x times the partial of x with respect to t. Again, that's a partial because it depends on two variables. Plus the partial of w with respect to y times the partial of y with respect to s. Okay? So that's your derivative with respect to one of the independent variables. Here's the partial of w with respect to the other independent variable. The partial of w with respect to t will then be the partial of w with respect to x times the partial of x with respect to t plus the partial of w with respect to y times the partial of y with respect to t. So here schematically, if this is helpful to you, okay, there's nothing wrong with it. The partial of w with respect to s, okay, we're only going these routes. So it's partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y times the partial of y with respect to s. You don't go this way because you're not doing it with respect to t. But if you are going with respect to t, it's the partial of w with respect to s times the partial of x with respect to t, or the partial of w with respect to y times the partial of y with respect to t. There it is. Okay. Make sense? Goodness gracious. You know what? I just realized this should have gone straight to example 2, not to the theorem. So let's back up a little bit and go do example 2. Then we'll come back, maybe repeat the theorem or just show it to you again and then do something with that. So here's two objects are traveling in elliptical paths given by the following parametric equations. X sub 1 is equal to 4 times the cosine of t. Y sub 1 is equal to 2 times the sine of t. X sub 2 is 2 sine 2t, and y sub 2 is equal to 3 cosine 2t. Okay. I know we've only been going about an hour, maybe a little less, but I think I'm going to have to get something to drink because I am really dizzy feeling. And I think I need a little bit of sugar. So can we pause here? I'll try to go on and wrap up later. If we need to stop again, we can, but I'm going to have to get something to drink, number one, and also probably a little caffeine. That today, and then we've got 3.6 directional derivatives and gradients, which is a fairly long section, and then tangent planes and normal lines is long enough. It's not quite as long as the other, and then extrema of functions of two variables, And that's a fairly long section. And then applications of a stream, I think we will not do that section. That's 13.9. And Lagrange multipliers, we won't do that. 13.10. And then, yeah. So I'll just basically, yeah. So it's a bit off. Maybe next week, but I'm guessing more likely the beginning of the following week. Okay. We'll see. Now, and while we're on that subject, I think part of my dizziness, too, is these glasses, because my distance vision is great without the glasses, but my close vision is terrible without the glasses. So when I put the glasses on, my distance vision gets really lousy. So I think going back and forth, it's kind of driving my brain crazy. But to ask you, to remind you of this little feature, it's kind of a good news, bad news situation coming up. The bad news is next Thursday, not tomorrow, but next Thursday is the 4th of July, and that's a state holiday. There's no school on next Thursday, on the 4th. The good news is it doesn't affect us any because we meet Monday and Wednesday. So, yes, okay, we got that down. Okay. Yeah. So, anyway, we'll be in good shape. All right. Let's go on with this one. I'm feeling a little bit better, but I really do think a lot of it's these glasses because y'all look so fuzzy, and the print is good, and that's in between being fuzzy and good. But I just can't keep taking them on and off all the time. So anyway, here's example 2. Okay. 2 objects are traveling in elliptical paths given by the following parametric equations. X1 and X2 are one elliptical path, and X1 and Y1 are one, and X2, Y2 are the second. At what rate is the distance between the 2 objects changing when t is equal to pi? The rate at which the distance between the 2 objects is changing, okay, when t is equal to pi, okay? It could be increasing, decreasing, that could be a positive or a negative rate, either one, okay. Now, the distance between the 2 objects, that's going to be our independent variable, okay? But we don't have that, okay? So we need to come up with what that is. And they use the symbol S. S is the distance between these 2 objects. And if you remember from your distance formula, S is the square root of x2 minus x1 squared plus y2 minus y1 squared. Remember that from somewhere deep in the past? Distance formula? Make sense? Okay. Plug in what those are from up here. It doesn't matter which which ones we put first and second or anything else, but I'll just write it the same way I've written it here. So that would be 2 sine of 2t, that's x2, minus 4 cosine t squared plus 3 cosine 2t minus 2 sine t, if I can read my writing, squared. There's the distance at any time t. And what it's asking is, at what rate is the distance between the 2 objects changing when t is equal to pi? The rate at which the distance is changing. Okay? So that is partial of s with respect to, now there's only one independent variable, so let me back up and change that. Okay. ds dt, because the rate at which it's changing is how the distance changes per unit time, which is ds dt. Now what that is, let's not go to this one because that's really complicated. Let's use this one, okay? And that will be just this one here. What is the, okay, let's write it down. Partial of s with respect to x1, okay? You're going to have to do this for each one of them because like they said before, let's go back, not back here. I'm going to come back to this in a minute. Like they said here, we do it. Here we have 4 x's here. Literally x1, x2, and y1, y2. Those are going to be our 4. So we're going to do our partial derivative like they did there with 4 of these. So here's what it is. Partial of s with respect to x1 times dx1 dt. Right? You tell me the second term. Anybody? Starts the same way. Partial of s with respect to x2, derivative of x2 with respect to t. Because you see x2 is a function of single variable t. Okay? Next. A little louder. Partial of x, s, no, y. Oh, did you do y last time? Yeah, there's 2 x's and 2 y's. I can't hear, so if you say y1, I can change it.
Oh, no.
Okay, well then let's do y1 now. y1 times dy1 dt plus s with respect to y2 times dy2 dt. Perfect. Now we got to work out what each one of those are. Now I'm going to rewrite this equation here before we do it, just to make it easier to do. Okay, this is going to be, let me put it in bracket, x2 minus x1 squared plus y2 minus y1 squared to the 1/2 power. I think that's easier to take the partial of. Let me clean this up just a little bit, okay? So let's take the partial of that with respect to x1. Partial of s with respect to x1. Yeah, this is the s. S with respect to x1. Is what? Yeah, in fact, a bunch of chain rules here. Let's start with the outer. Be 1/2 times x2 minus x1 squared plus y2 minus y1 squared to the minus 1/2, right? Then chain rule this where the x1 is, so that's going to be times a 2 x2 minus x1, and then because it's respect to x1, we're going to have an additional minus sign. So we're going to put the minus out here. I think I covered it all, okay? Yeah. The other terms don't have that in it, okay? Now let's clean that up just a little bit. The 2's can go out from here, okay? And I think the rest of it will stay pretty much as is. All right, now we got to multiply that by dx1 dt. So that's going to be multiplied by, here's your x1 right here. What's the derivative of that with respect to time? Negative 4 times sine t. Okay? Now that means the minus signs can go away. Okay? Okay? Now let's do a plus. And we're going to do the partial of s with respect to x2. That's going to be very similar to what we just did. So it's going to be 1/2 the x2 minus x1 squared plus y2 minus y1 squared to the minus 1/2. So that part's just the same. Okay. Times the 2 times x2 minus x1, that's going to be the same. The only difference is it's going, we don't have the minus sign. Now I'm trying to figure out how I wound up with something canceling out the minus sign before. Oh, yeah, I know how. Okay. Don't worry about that yet. This will disappear. The 2's go away. Okay. I think I've got too many closed bracket symbols here, but I think that's okay. We'll straighten those out later. Now we have times dx2 dt, and what's that? Here's the x2 dt. Second? That's an equal sign. That's not a minus. Derivative of sine is cosine. So it's not minus, but it's going to be 4 because you have the 2 out here and the 2 in there. 4 cosine 2t. Okay? Now, plus, now we've got to do this one, the partial of s with respect to y1, and that's going to start off the same way, 1/2 times x2 minus x1 squared plus y2 minus y1 squared to the minus 1/2. That starts the same. But this time is with respect to y1, so then this one will be times a 2 times y2 minus y1 to the first power times a minus sign. So this then will change that to a minus. so far. Okay, hang on, we may still get there. Okay, that's this part. Now we do dy1 dt. Well, that's from here. And what's that? Two cosine t. All right. Yuck. So that would quit. Well, first the 1/2 and the 2 go away like they have been going. Okay, and we wound up with a 2 there. We'll worry about that later. Now, the really bad news is I don't have room at the bottom of the page to do the last one, but I think I can get it in maybe. All right, so the partial of s with respect to y2 is going to be just like we started before, 1/2. So I'm going to start with a plus. I'm going to try to start with a plus. There we go. 1/2 times x2 minus x1 squared plus y2 minus y1 squared to the minus 1/2, okay, times derivative of what's on the inside, and that's going to be a 2 times y2 minus y1. Then this is respect to y2, so that's going to be a positive. Okay, so that stays positive. Okay, times dy2, that's this one right here, dy2, well, lost an equal sign there, dt. What's that? Derivative of y2 with respect to t. Can you see it? Anybody? Help me, I'm drowning up here. Okay, it's going to be a minus, because its derivative of cosine is, it's what? It's going to be a sine of 2t. I have to let my n show up so I can tell where to put my 2t, but it's got a coefficient. Okay, I put the minus 6. Perfect, perfect, perfect. Okay. Now, again, the 1/2 wipes out this, and I'm going to take this minus sign and put it up front. Okay. Goodness gracious. Now, this is one long, hairy problem. Okay? Now, you could combine a lot of things together, like factor this out because it shows up in every term the same way. Okay? And these two could go together because they show up in both terms the same way. These two could go together, they show up the same. And you could have changed your others, but let's not do that for right now. Let's evaluate this like it said when t is equal to pi. Okay? In fact, they did it before we got this far along. Okay? In fact, I don't see, I see how they did. Okay? So let's do, you're trying to do this all at t is equal to pi. I forgot to write that down. What is the rate of the distance when they're changing? And this is all at t equal pi. We could have probably saved ourselves a little grief here. So let's do it. Let's do x1 when t is equal to pi. And that would be what? What is cosine pi? Second? I don't think so. -1. So this will be -4, right? Let's do y1 at t is equal to pi. What is sine of pi? 0. All right. Let's do x2 when t is equal to pi. Ew, yuck. Okay, yeah, I know. Well, I've got to get this. Okay. T is equal to pi. My pen is so slow. And that is, again, 0. Okay. And y2 when t is equal to pi. Yuck. Okay. And that would be, second? I think it's just 3, isn't it? Because when t is equal to pi, 2t is equal to 2 pi, right? Cosine of 2 pi is the same as cosine of 0, which is 1. 1 times 3 is 3. Okay? All right. Now that we know those, we can make life a lot better. But let's also figure out what S is when t is equal to pi. Okay? So S is equal to the square root of x2 minus x1. Well, x2 is 0 minus x1, which is a minus 4, so that is going to be 4 squared, which is going to be 16. Right? We'll get there in a minute. Plus, oh man, y2 minus y1, that's 3 minus 0, so that's going to be 3 squared. And I don't need that big a thing here. Let me make that a lot smaller. Now, anyone know what that is right off the top before you do all the calculations? Whoops. Okay, that's going to be the square root of 25, which is 5. So your S at t equal pi is going to be 5. Okay? Now, with that in mind, I think we can go back and simplify these things considerably. So let's do this line right here. Now remember, this was our 5 here, remember, as a 1/2, but with the minus sign it's 1/5. Okay? So this thing right here is going to be 1/5. Okay? Times, and the x2 minus x1 was 4. And the 4 times sine of pi is going to be 0. Huh. All that to get you to 0. Okay? In fact, the only two that are going to contribute anything are going to be the two with the cosines in them. Okay, so let's just jump to those. Because you see, this one's going to be 0 when t is equal to pi. Okay, so let's go and do these. Again, this is going to be a 1/5. Okay. And then we've got a x2 minus x1, which was 4. And then we've got a cosine of 2 pi is 1 times 4 is times another 4. Okay? Now this one is going to be a 1/5. Oh, it's going to be a minus because of that minus sign there. Okay? And this is going to be y2 minus y1, which is 3. And your 2 cosine t, well, your cosine of pi is minus 1 times 2 is minus 2. So this is minus 2. So when we add all those things together, this is 16 pi plus 6 pi. That's not pi. 16 fifths plus 6 fifths. That's 21 fifths, isn't it? Now, I don't know if that's the answer they get. Yeah, oh, they get 22 fifths. I missed one. Okay, let me go back and see. 6 fifths plus 16 is 22 fifths. I can't add. 22 fifths. My word. Okay, how long and involved that is. Now, it probably would have helped if I had gone on and plugged in the pi, t equal pi much earlier. But you can't do it too much earlier because you have to have your things here, because if you plug it in too earlier, then this is going to be a 0. Everything's going to be a 0. So you have to keep them for a little while, but then plug in. So I probably kept them a little too long, but we got a 22 fifths. All right, so that was example 2. Now I think we also have example 3 to go. So let's erase these. All right, and do example 3. Any questions? I should have asked that before I erased. All right, example 3. Okay. Here's what it says to do. Find partial of W with respect to S and partial, let's see, I'm a little confused here. I'm going to page up a little bit and see what's happening here. Nope. Oh yeah, I'm sorry. That was the wrong one. Already did that. 13. Nope. Somewhere in here we have to do example 3. So here's example 3. We want to find partial of W with respect to S and partial of W with respect to T. For W is equal to 2xy Sx is equal to s squared plus t squared, and y is equal to s over t. Now I'm going to write that slightly differently. S times t to the minus 1. That's just the t to the minus 1, not the product. Okay? Now, it says find the partial of W with respect to S. There's 2 ways you can do it. Name one of them. And what was that? It's what? A little louder, I can't hear. Okay, dw over dx, is that what you said? Times partial of s with respect to t. I mean, x with respect to s. I can't write. Goodness gracious. And s and x sound so close together. Okay, let me get this. Partial of x with respect to s plus partial of w with respect to y times partial of y with respect to s. Perfect. Okay? Now, we need to do each of those. What is partial of w with respect to x? There's your w. Partial w. Huh? No, 2y. Because you're taking with respect to x. Treat 2 and y like they're constants. Derivative of x would be 1, so that would just be 2y. Right? Okay? And we also need partial of x with respect to s. What would that be? 2s. Perfect. And we also need the partial of, ultimately, we're going to need the partial of w with respect to y. I can't write. What would that be? 2x. And we'll also need the partial of y with respect to s. It's what? 1 over t? Yeah, 1 over t. All right. So we can plug in here. And the partial of w with respect to x is 2y. Now, just to save a little bit of time here, let's just go on and plug in what y is. It's 2 times s over t. Okay? Times dx ds, that's 2s, plus, and the partial of w with respect to y is 2x, so that's 2 times s squared plus t squared times the partial of y with respect to s. There it is. And that's 1 over t. Right? Okay. So let's clean that up a little bit. And in the first term here, we get 2s times 2s is 4s squared over t plus 2s squared plus 2t squared also over t. So this will be 6s squared plus 2t squared over t. And that looks like a good way to leave it. And that's what they got too. Okay? Now let's do the partial of w with respect to t. Partial of w with respect to t. And that's going to be what? Get out of there. Partial of... Second? Okay, we just did this one. Now we're doing this one. So you want to just plug in? That's going to be the partial with respect to x, which is 2y, which we'll put. Is that what you meant?
No, sir.
Huh?
No, go ahead.
That wasn't skipping too many steps. Okay. I see what I thought that's what you meant. And I was like, I'm all in favor if you are. This is partial of w with respect to x again, which we're going to plug in just like we had before. But this time it's times partial w with respect to t, the partial w with respect to x times the partial of dt, or is partial, because they're two independent variables, plus partial of w with respect to y times partial of y with respect to t. Okay, now this time, get out of there. This time we've already got these done, that one and this one. Those are already done. We just need to do our partial of x with respect to t and the partial of y with respect to t. So let's do that somewhere here. The partial of x with respect to t is from here, 2t. And the partial of y with respect to t, and that's over here. That's going to take a little more work, minus I thought you said minus, sorry, minus s t to the minus 2, right? Because it's taken with respect to t, this one right here, minus 1 times s times t to the minus 2, right? All right. So I'm going to plug them in down here. The partial of w with respect to x we had here, we had up here, and we found that to be 2s over t, wasn't it? Yeah. No, it wasn't. It's 2s. Where is it? Oh, yeah. Y was 1 over t. So it's 2y, so that would be 2 over t. No. Don't tell me I messed that up. All right, we got the right answer. It's 2y, but y is s over t. So yeah, that's 2s over t times dx dt. Goodness gracious. Dx dt is 2t plus, and dy dt, partial w with respect to t, is this one, 2 times s squared plus y t squared, I can't write, times, that would be your minus, so let me change this to a minus, times s over t squared. Okay. We used these two because that was the w dx, and here's the w dy. We had already done those, so we just plugged those in down here. And then we did our partial of x with respect to t here, and the partial y with respect to t there, moving the minus sign across. So let's simplify these a little bit. And you got 2 times 2 and the t's are going to cancel out, so that's going to be 4s, that looks pretty simple, minus it looks like a 2s cubed plus, well, minus well, they kind of do, but we're going to need to put everything over t squared anyway. So 2s cubed minus 2st squared all over, no, just these parts over t squared. And then we're going to have to put a t squared here to make that over t squared. Okay, because that wasn't over t squared before. So now these combine to be 2st squared minus 2s cubed over t squared. Now you could fiddle with the first term, but they don't. They leave it as 2ts squared minus 2s cubed over t squared. And that's just about as simple as you can do. Oh my goodness. Okay. Now, what they did was substitute first and put the w is equal to 2xy. They plugged that s times that y, and that got to be whatever that was, and then they did the partial with respect to s and the partial with respect to t. And I'm not sure that's any better. This was pretty easy. There were a lot of steps, but it was pretty easy steps. When you put it all together, then you've got a quotient rule and other things like this. Pay your money and take your choice. You've already paid your money. Either substitute first and then do your derivative, or do your derivatives like we did and then plug them in. Okay? You got to do both steps at some point. So I didn't do it quite the same way the book did, but we got the same answers. Okay? Now, like I said, I jumped ahead before I realized they had skipped examples 3 and 4. So we'll go back over. And that was our chain rule for 2 independent variables. We already went over that. So now we're ready for example 4. Okay, and this is where we're at. Okay, it says use the chain rule to find the partial of w with respect to s and the partial of w with respect to t for w. Wait a minute here. That is exactly example 3, and we did it with the chain rule because I wasn't paying attention. They want us to do example 3 by substitution, and we talked through that, but just briefly. And now they say do the very same thing using the chain rule, and that gives exactly the same answers we just did. Okay? Now, you decide which one's easier. I think the chain rule was, but we didn't do the other one completely, just because the derivatives are easier with the chain rule. We wrote that down first, just like they did here, and then we plugged in what the partial of w with respect to x and partial of x with respect to s and all that kind of stuff, and we got that same answer here, 6x squared plus 2t squared over t. And then we, holding s constant, we did the partial with respect to t, and that was those values. And that would be 4st squared minus 2st squared is 2st squared minus 2s cubed, all of that over t squared, and we got the very same answer we did before. Sorry, I wasn't paying close enough. I didn't know they were going to ask for everything all over again. All right, the chain rule in theorem 13.7 can also be extended to any number of variables, either as independent variables or intermediate variables, okay? Woo, it can be messy really fast, okay? As we saw with the S's and T's and X1s and X2s and all that kind of stuff. So if you have one dependent variable W, and you have a multiple of intermediate variables, X1, X2, X3, all the way up, you do one as you're doing this with respect to T1, and you have a bunch of T's too, by the way. So do it for T1, and that'd be partial of W with respect to X1 times partial of X1 with respect to T1, plus partial of W with respect to X2, partial of W with respect to T1, W X2, T1, all the way up to partial of W with respect to Xn, and the partial of Xn with respect to T1. And then do it all the way down for all M of your T's, because you have M T's and N X's. It gets huge fast. Most of the time, we're not going to have more than 2 or 3 of those and 2 or 3 of those, most of the time. So don't let the enormity of this bother you. How do you eat that 5,000-pound elephant? One bite at a time. Just take it one step at a time. Okay? Now, I think we're ready for example 5. They're not showing example 5, so we have to back up and do example 5. All right. Okay, we got another hour, right? Okay. Isn't this so much fun? So, what we're looking for now, surprise, surprise, is partial of W with respect to S and the partial of W with respect to T when S is equal to 1 and T is equal to 2 pi. Okay? For, here's the function W. W is equal to xy plus yz plus xz, where x is equal to s cosine t, y is equal to s sine t, and z is equal to t. Okay. These enough pieces? Okay. Oh my goodness gracious. Let's first write down what our partials are. The partial of W with respect to S. What does that be? Partial of W with respect to X times partial of X with respect to S plus partial of W with respect to Y times the partial of y time with respect to, same thing you have here, s, okay, plus the partial of w with respect to z, right, times the partial of z with respect to s. Done. Let's write down what the partial of w with respect to t is. Starts the same way. Anybody? How does it begin? Partial of, help me, w with respect to x times the partial of x with respect to, second, t, perfect, plus partial of w with respect to y times partial of y with respect to t, plus w with respect to z times partial of z with respect to t. Okay. Done. Now, just as before, let's do our partial of w with respect to x. But while we're doing that, we're also filling what x is, what x and y and z are. So the partial of w with respect to x from this, what would that be? Y plus z, is that what you said? Perfect. And what is your y? No, it's s sine t, right? And what's your z? T. Okay. So let's do our partial of w with respect to y. And what would that be? X plus z. So that would be, your x is s cosine t plus t. Okay? And now let's get out of there. Okay. Let's do the partial of w with respect to z. And that would be, I've lost it, there it is, or x plus y or y plus x. And that would be s cosine t plus s sine t. Okay. Now, let's do the partial of x with respect to s. Partial of x with respect to s. Right here. What would that be? Partial of x with respect to s. Cosine t. Perfect. That's why we're doing that. Let's do partial of y with respect to t. No, with respect to s. Sorry. I was going to say, why is that wrong? Okay. To respect to s. Goodness, my eyes are aching. To respect to s. What would that be? Sine t. And the partial of z with respect to s is 0. Absolutely right. Now, I've got to find a place to do the others. The partial, I'm going to take off that line. It's just in my way here. Okay. Usually I leave it in there, but not now. The partial of x with respect to t is going to be what? Negative s sine t. Perfect. Partial of y with respect to t is equal to s times cosine t. And the partial of y with respect to t. Partial of z. Goodness gracious, where did y come from? It is getting late in the day. Goodness gracious, I can't believe partial of z with respect to t is 1. Good. I think we have all the pieces. Let's fill them in. And we want to do this when s is equal to 1 and t is equal to 2 pi. Okay? Now, let's go on and figure out what these pieces are then, so we don't have to write as much. When s is 1 and t is equal to 2 pi, this is 1 times, what's the sine of 2 pi? Second? 0. Okay? Plus t, and when your t is 2 pi. So this is just going to be 2 pi. Okay? The w dx is going to be, partial of w with respect to x is going to be 2 pi at this value, these values. Okay? Now, partial of w with respect to z at these values, or your x, is going to be 1 times the cosine of 2 pi. What's cosine of 2 pi? Cosine of 2 pi. Sine of 2 pi is 0. 1. Okay, so it's 1 times 1 is 1. Okay? And the partial of w with respect to z is going to be x plus y. I should have been putting these over. Okay. It's okay. And this is going to be 1 times cosine of 2 pi is 1 plus, second, 0, because sine of 2 pi is 0. Okay? Okay? Cosine of t is, of 2 pi is 1. Sine of 2 pi, 0. Okay, right, I got a 0 there. Minus 1 times the sine of 2 pi is sine of 2 pi is 0. And 1 times the cosine of 2 pi is 1. Okay? And then dz dt is 1. So I think we can just plug and chug, folks. Okay? The w dt is 2 pi. I mean, the w dx is 2 pi. Times dx ds is 1. So that's just 2 pi. Plus dw dy is 1 times dy ds is 0. So that goes to 0. Plus dw dz, or partial w with respect to z, that is 1 times partial w with z with respect to s is 0. So this one's just 2 pi. Whew, all that for that. On the next one, partial of w with respect to s, x is 2 pi, times partial of x with respect to t is 0. So that disappears. Plus partial of w with respect to y was 1 times the partial of y with respect to t. And that's 1. Okay, so that's just going to be 1 plus partial of w with respect to z is 1 times dz partial of z with respect to t, and that's 1. So you got 0 plus 1 is equal to 2. Now, all right, here's Carlton. Okay, we're on example 5 on page 915 in section 13.5. Chapter 13 is functions of several variables. 13.5, chain rules for functions of several variables. And we just were wrapping up example 5, but I made a mistake somewhere, I think, and I'm trying to find it. We got the partial of w with respect to s, right? That was 2 pi. For partial w with respect to t, our dx dt, I thought we got to be 0. Yeah. Oh, it's the second one. Okay, I'm kind of lost here. The partial of w with respect to y I think that's the one I messed up, is x plus, that's where I messed up, plus z is wherever it was here. Z is t, and t is 2 pi. I forgot to put that one in. I was writing here, it's 1 plus 2 pi. That's where I messed up. So this is 1 plus 2 pi times 1. Okay. And then we have, the last one is 2. So that would be okay. It's 1 plus 1 is 2 plus 2 pi. Okay. Yeah, and we got it. Good. I had not written that out. I started writing and realized I was writing over the wrong letters, and I forgot to go back and write over the correct letters. Whew. Those things can take a little bit, okay? And you have to be very careful with your bookkeeping. All the little pieces are easy, but it's sort of like Legos. You know, there's lots and lots of little pieces, you know, so don't be missing any. All right, so there was example 5. We did it on example 4 space because we didn't have room here. So let's get through with 4 and that. Now let's move to implicit partial differentiation. This section concludes with an application of the chain rule to determine the derivative of a function implicitly. Okay? Let's let x and y be related by this equation, capital F of xy is equal to 0, where y is equal to some function of x, that's a differentiable function of x, y is. And to find dy dx, you could use the techniques discussed way back in 2.5 when we talked about implicit differentiation of single variable functions. And you'll see, however, that the chain rule provides a convenient alternative. Consider the function w is equal to this f of x, y, not necessarily that one, which is this function f of x, f of x, where little f of x is y. Like I just told this somewhere here. Yeah, right here. Y is equal to f of x. So you can apply last theorem to this, dw dx, because you only have one independent variable now if you write y as a function of x. So dw dx is the partial of f with respect to x, dx dy, plus the partial with respect to y times dy dx. Well, dx dx is 1, okay? dy dx is what, is not necessarily 1, okay? Now, oh yeah, I was wrong. We are still saying, goodness, I already lost it. Okay, that this w which is f of xy, they're saying that is indeed equal to 0. Okay? Now, w is, that doesn't mean the partials are. Okay? So, but w is, and if w is, then the partial of w with respect to x, well, we don't know. Because w is equal to f of xy is 0 for all x's in the domain of f, you now know that the w dx is going to be 0. Okay? So if the w dx is equal to 0, then you have f of xy times dx dx, which is 1. Why they keep writing it that way, I don't know. Plus f of y, xy dy dx is equal to 0, because the w dx is 0. Now, if the partial of f with respect to y is not 0, you can use the fact that dx dx is 1, which I've been saying all along, and conclude that the dy dx is equal to minus f of x dx divided by f of y x xy over f of y xy. Now, it's sort of an interesting approach, because if you think of your capital F here, partial of f with respect to x, this is partial of f with respect to y, you would think the partial of f would cancel out and these would flip over and you get dy dx, but you don't. You get a minus sign. But otherwise, it's correct. Similar procedure can be used to find the partial derivatives of functions of several variables that are defined implicitly. Okay? So, I don't necessarily recommend trying to memorize this. I recommend doing the partials unless they get really nasty, and then come back and do this. So I think this is going to be expressed here as your chain rule for implicit differentiation. Okay? Now, if the equation, capital F of xy is equal to 0, defines y implicitly as a differentiable function of x, then dy dx is equal to the partial of f with respect to x minus the partial of f with respect to x over the partial of y with respect to x. Partial f with respect to x over the partial of f with respect to y. As long as this thing here is not 0. If the equation f of x, y, z is equal to 0, define z implicitly as the differentiable function of x and y, then what you have is dz dx is minus partial of f with respect to x over partial of f with respect to z, and dz dy would be partial minus the partial of y, f with respect to y, over the partial of f with respect to z. And in both of these cases, that partial with respect to z can't be 0. Okay. So, supposedly that's going to make it simpler. Let's see if it does. Example 6. Here's a function. I hate to call it a function. Here's a relation. Y cubed plus y squared minus 5y minus x squared plus 4 is equal to 0. They want to know what dy dx is. Okay? Now, let's do it the way we did back in Cal 1. I'll just put it that way because y'all may have been in different books. How would we do this? Do you remember? You don't have to use partials here. Let's just do it the way we used to. How would that go? Take derivative of this with respect to x. 3y squared y prime, okay, plus y prime, because of chain rule. Next, minus 5 y prime minus 2x, take derivative with respect to x, is equal to 0. Perfect. Now let's gather all the y prime terms together and move all the ones that aren't y prime to the other side. So this would be, I'm going to factor out the y prime to boot. So it's going to be 3y squared plus 2y minus 5 all times y prime is equal to 2x, right? I moved the term without a y prime over there. So now we get y prime is equal to 2x over 3y squared plus 2y minus 5. Okay? Now, that was pretty easy. Okay? Now, I don't know why for sure they're wanting us to do it with some big function, capital F of xy. But that's what they want us to do. So we're going to call this thing here F of xy. Okay? Now, what they tell us to do with this is dy dx, remember the rule, minus f sub x of xy over f sub y of xy. Now, let's go back to this for just a minute here and notice. If you're doing dy dx, put the x with respect to x on top here with respect to y down here. If you're doing partial of z with respect to x, do the f sub x up here, the f sub z down here. partial z with respect, and always keep the minus sign. Remember, they always have a minus sign. The partial z with respect to y, put the partial with respect to z down here, partial with respect to y over here with a minus sign. Okay, and so on. Okay. Now, so let's go back and do ours here. So that's what we did. Partial of f with respect to y in the denominator, partial of f with respect to x in the numerator. Well, let's do what partial of f with respect to x is. What would that be? There's your f of xy. What's the partial with respect to x? Here's your f of xy. Take the partial of that with respect to x. These terms don't have any x's, so those would be zeros. This would be a minus 2x. Okay? Now let's take the partial of that with respect to y. 3y squared. Say again? Plus 2y minus 5. So they say, let's just write it this way, minus your f with respect, partial of f with respect to x. That's a minus, so that becomes a 2x over partial of f with respect to y, 3y squared plus 2y minus 5. So if you remember this formula and then do your partials, yeah, that can be just as easy as this, maybe a little easier. But you got to remember the formula, remember with the minus sign in it, okay? So there you have it, okay? All right, I think that's done. Oh, let's watch them do it, okay? All right, to erase? Okay. Begin by letting the f of xy be that very function there, because that's equal to 0. Now, if this thing was done with that equal to minus 4, move your minus 4 over, set it equal to 0, then do it. If it was there with an x squared minus 4, then move it back, and so get it so it's equal to 0. Then do your partials. Partial of x is only the minus 2x term. Partial of y would be those terms there. And then write down from the theorem, dy dx is equal to minus the partial with respect to x on top, the partial with respect to y on the bottom. Plugging that in, it's a minus 2x over 3y squared plus 2y minus 5, which is the same thing we got when we did it the other way. Okay? The other way was pretty easy. Now, if you have a bunch of mixed up terms here, then this way probably turns out being much easier. All right. So this is skipping example 7. So let's go back and do example 7. Okay? Find partial of z with respect to x and the partial of z with respect to y. Partial of z with respect to x and partial of z with respect to y. For 3x squared y, no, that's 3x squared z, I can't read. Minus x squared y squared plus 2z cubed plus 3yz, yuck, it's not y to the z, that's 3yz, I don't know what's going on here, 3yz minus 5. is equal to 0. Okay. So there's your function equals 0. So since that's equal to 0, we can write this down as being our capital F of x, y, and z. All right. Now we're wanting the partial of z with respect to x. Can you write down for me what that's going to be? I'll lead off. Minus. F sub x of x, y, z over see, you put the one up here. The one that's down here, you put up here. The one that's up here, you put down here. Okay, can we go on and write down what partial z with respect to y is? Okay, you put the minus, don't forget the minus, f sub y of x, y, z over f sub z of x, y, z. Okay, so sounds like what we got to do is take some partials, right? So let's come over here to the side and take a few partials. Let's first do the partial of f with respect to x. Okay, of that function right there. What would you say it is? A little louder. 6x at z. 6xz. You count z as if it's a constant. Remember? Okay. Next. Minus 2x y squared. Perfect. Next. There aren't any because there's no more x's in there. Okay. All those are treated as constants. Okay. Let's do our f sub y. Going back up to the top, what would that be? Okay, minus 2x squared y. Is that what you're saying? All right. Next, plus 3z. Perfect. Okay, and the last one, f sub z. 3x squared plus what? 6z? 6z squared. Perfect. Plus 3y. Excellent. Okay? So now we can just plug and chug, right? Partial of z with respect to x is equal to minus f sub x, which is okay, I'll put the minus down. F sub x. Okay, you're going to reverse the order. So I'm going to change that to a plus, and we'll change the order and make it 2xy squared minus. If you're reversing the order and losing the minus sign, then keep the signs have to be different. Okay, 6xz. Now you flip that one, so don't flip the next one. Well, there's nothing to flip there. You just write down 3x squared plus 6z squared plus 3y. Now, I don't know if it's worth it, but you could factor out a 3 out of the denominator and a 2 out of the numerator if you wanted to. I'm not saying it's worth it. That would be 2/3 times xy squared minus 3xz over x squared plus 2z squared plus y. There's no advantage to doing that, but it is something. There's a common factor here and a common factor there. You could pull it out. Not necessary, but you could do it. Okay? Now, can you see? Okay. Let's do the second one. Partial of z with respect to y. What goes where? Minus, I'll put there. A little louder, I can't hear. Okay, I'm going to take off the minus sign and negate that. So I'll say 2x squared y minus, okay, minus 3z. They have to be opposite signs, okay, over, yeah, and you could pull out the 3, but 3x squared plus 6z squared plus 3y. And if you wanted to, you could call that as 1/3 times 2x squared y minus 3z over x squared plus 2z squared plus 3. There's no advantage to doing it that way, but you could. And they don't. Okay. They leave it the first form that we had, 2xy squared minus 6xz over 3x squared plus 6z squared plus 3y. And then the second one, partial z with respect to y, they left it as 2x squared y minus 3z over 3x squared plus 6z squared plus 3y. Great. Okay, that finishes 13.5. Homework exercises here include either 3 or 5. They're both at Calc Chat. 3's at Calc View. Any of the odds 7 through 11, they're all at Calc Chat. 9's at Calc View. Do 13, which is only at Calc Chat. 15 or 17, which are both at Calc Chat. 15's at Calc View. 19 or 21, which are both at Calc Chat, but 19's at Calc View. 23 or 25, they're both at Calc Chat. 23's at Calc View. Any of the odds 27 to 33, they're all at Calc Chat. 31's at Calc View. Either 35 or 37, they're both at Calc Chat. Either 39 or 41, they're both at Calc Chat. And by the way, here they go again. They put definitions and stuff in the homework exercises that I don't see why they didn't put in the regular section, but they didn't. So this is just talking about a homogeneous function. It gives you a definition for it. Okay, so 39 or 41, they're both at Calc Chat. 43 should be at Calc Chat. You can explore doing either 45 or 47 if you'd like. They're both at Calc Chat, or should be. And then any of the odds 49 to 55. Now 55 is one of those homogeneous functions, which was from up at the top of the page on the left-hand column. So you can do any of those you want to. Some of those we haven't done anything like it, but they give you everything they need. All right. Any questions on those? All right. That finishes 13.5. So that means we're going to leave this, all right, to erase this? Okay. Going to discard this and pick up 13.6. This is one long chapter, folks. But like I said before, this is one of the key chapters, I think, in Cal 3. Partial derivatives. The other really key chapter is multiple integration. Okay, then after that we'll do some things, if we have time, that build on these. But these are the keys. All right, so I can't find my thing. Go from current slide. All right, we've seen that before, chapter 13, functions of several variables. 13.6 is directional derivatives and gradients. All right. when you have a function of one variable, y is a function of x or something like that, then you talk about how y changes when x changes, and that gives you derivatives, right? Positive derivative, zero derivative, negative derivative, whatever, right? But when you have functions of multiple variables, okay, here you have a surface here as a function of x's and y. Here's your z's up here. Well, if you're going this way, your gradient, your derivative may be like that, but going this way, your gradient may be like that. You know, the surface could be going like that, okay? So that's what we're talking about with directional derivatives, and that will later define or use those to define what is a gradient, which is a pretty useful concept in three-dimensional physics, which is where we live, is 3 dimensions, or 3 or more dimensions, by the way. So here are our objectives in this section. We'll find and use directional derivatives of a function of 2 variables. Then we'll find the gradient of a function of 2 variables. Then we'll use the gradient as a function of 2 variables in applications, and then we'll find directional derivatives and gradients of functions of 3 variables. We'll stop at 3, okay? Although you could go on, but it really gets hard to visualize because we live in 3 space. We don't live in higher dimension spaces than that. Okay, so let's first talk about what in the world a directional derivative is. Say you're standing on a hillside, represented by z is some function. Z is the elevation of that hill as a function of x and y, which is some plane down here underneath the hill. You can't see, but it's down there. Say at the base of the hill, you have a plane down there, and that's your xy plane, okay? And you want to determine the hill's incline toward the z-axis, okay? You already know how to determine the slopes in two different directions. The slope in the y direction, given by the partial root of alpha sub y of xy, and the slope in the x direction, which is given by the partial derivative of L sub x and xy. In this section, we'll see that these 2 partial derivatives can be used to find the slope in any direction, okay? So if this is your y, the slope as change of z, or your function f, as y is changing from up here, that's slightly negative, okay? Over here, it'd be much more negative. Down here, it's a little more slightly negative, or here, okay? That's if you're on the y-axis, but if you're over here, it could be here, yeah, you see that, okay? Now, your partial derivative with respect to x is how is z changing when you're increasing x. And that, again, from up here, it's mostly downhill. Some of it's steeper, some of it not as steep. From over here, it's not maybe as steep, but it's still pretty much downhill. Maybe over here you're going uphill a little bit, okay? But those are your directions. Now, if you want to find the slope in any direction, that's what your directional derivative is going to help you with. So determine the slope at a point. Now, don't let me get too carried away here. At a point on the surface, you will define a new type of derivative called a directional derivative. So let's begin by letting z equal alpha of xy. That's some surface up here as a function of your xy plane down there. Z is a surface. P is a point at the value x0, y0. So come out to wherever x0 is, okay, and y0, looks like y0 may be close to 0 here, very, very close to 0. X0 is a little bit here. There's your point P. Function of x0 and y0. Okay? Evaluated there. It's a point in the domain of F, there on that plane, xy plane, as shown in the figure. The direction of the derivative, of the directional derivatives, is given by a unit vector, Now this time the unit vector is called u, okay? It's not always the case, but this is a unit vector. If I was writing that, I'd put a little housetop on it to remind myself and you it's a unit vector. Well, this is cosine theta I plus sine theta j, which is what we're used to if you think about it. Because cosine, say, of a unit circle would be your y, your x component, and sine theta would be your y component. Okay? So here's your point P, okay? Your x component would be the cosine of that angle, and let's go back a minute here. Here's the unit vector in the direction of that vector. Now that was a very short vector because the y value was very small. X value was a bit bigger, but it didn't give you very much. But here, the unit vector would be in that direction, okay? And its x coordinate would be the cosine of that angle, which is the adjacent side, okay? So that would be this map, and the y value of the unit vector would be your sine of that angle theta. The sine of that angle theta it doesn't we're talking the unit vector here, not the vector that it's on. The unit vector is in that same direction, but it's this unit vector. Its x component is the cosine, which is the adjacent side, and the y vector is the opposite side, which is the y coordinate there. Okay. Okay. I'm going to take something back here. This P has nothing to do with that U yet. The U is just a unit vector somewhere there in the xy plane. Here is the point P, and you're going to refer to that in the sense of in the same direction as that unit vector U. So they've got sort of things backwards here, but that's what it is. This unit vector has nothing to do with the point P yet. We're going to come back to that. They just said begin by having a surface and a P somewhere there on the xy plane. Then let's just make up a direction, U here. That's the unit vector given by cosine theta. Why they keep referring to this angle, this to be the angle to be theta. It is the same as this one if those lines are parallel, but why don't they call it this? The x component is the adjacent side, y component is the opposite side. Okay? Sine. Okay. Now, to find the desired slope, okay, that we haven't said what slope they're talking about yet, reduce the problem to 2 dimensions by intersecting the surface with the vertical plane, passing through the point P and parallel to U. So that's what they were getting at back here. Here is the unit vector they were talking about, just randomly chosen to be in this direction. Okay? There was a point P happens to be there. So let's take a line parallel to that directional unit vector and make that line go through the point P. Okay? So that gives you the same angle as the unit vector U. Okay? That's the only connection now. The same angle, same direction as U. Okay? Now, to find the desired slope, reduce the problem to 2 dimensions by intersecting the surface of the surface that we have here with the plane that is along the line of the unit vector U that contains that point P. So here's that plane, that same line we had there, intersect that with the surface up here. Okay? Now, that vertical plane, this vertical plane now, oh, this one here, the one that goes through point P and the line is parallel to unit vector U. That vertical plane intersects the surface to form some curve C. The slope of the surface at this value, x0 on x, y0 on y, and then this f of x0, y0 up here, the slope here is going to be like that, okay? And that will be the slope in the direction of that unit vector we started with, which you don't even see on here anymore, but that would be that. In the direction of u is defined as the slope of the curve C at the point x0, y0, f of x0, y0. Z0 up here corresponds to those values. Z is equal to f of xy. Now, they introduced a new point Q in the picture here. They haven't told you why. What they told you is this looks like T units from P. But hang on to that. We'll get to that hopefully on the next slide. Okay? Informally, you can write the slope of the curve C as a limit that looks much like those used in single variable calculus. That sounds like a fun thing to do, doesn't it? The vertical plane used to form C intersects the XY plane in that line L. Now, they finally get around to telling you L. And L was pictured back here. That's that line L. It's parallel to this random unit vector here, parallel to that, going through the point P. There's the line L. They showed it to you back here, but didn't mention it until 2 slides later. They showed it here, but didn't identify it as L. But here they said that's the line L, represented by the parametric equations. X is equal to x0 plus t times the cosine of that same angle theta that we used to identify that unit vector. Okay? So x is equal to x0 plus t cosine theta, and y is equal to y0 plus t sine theta. Now, if we go back and look at this, that sort of is making sense, because here's the point x0, y0. So if you take the x0, add to that x, whatever value x you have, times the sine of the angle, that's the cosine of the angle, that's going to give you the how far out here on the x-axis, how much further that goes here. That parameter t tells you how much further you go there. And then the y0 plus whatever additional distance you go here on y, that's going to be y times the cosine of theta. The sine of theta, the adjacent side. I mean the opposite side. So the y is going to be y0, that gives you how far out from the x-axis you are. Then you add this t sine theta, which tells you how far out that line that's in the direction of theta you go. And this is t, that same parameter t times that cosine. Okay? So that for any value of t, the point q, x, y is also going to lie on the line L. Each of the points P and Q, P was the original point there, Q is any other point, there's a corresponding point on the surface up there. So that's Q. For P, there's a point up here. For Q, there's a point up here. Okay? Now, certainly these have two different directional derivatives because they're coming from different places. The direction part's the same, but the derivative, the slope, is going to be different. Okay? There's a corresponding point on the surface, x0, y0, f of x0, y0. We saw that one. X, y, f of x, y, that's the one over Q. Okay? Now, moreover, because the distance between P and Q on the xy plane there is x minus x0 squared plus y minus y0 squared, square root of that, we used that formula earlier today, remember? But the x minus x0 is your t cosine theta squared, and the y minus y0 squared is t sine theta squared. Now, where those come from, to remind you, is back here. If you do x minus x0 squared, that's t cosine theta. Y minus y0 squared is t sine squared theta, sine theta. And so when you take the difference of those squared, that's going to give you that. Well, guess what? Cosine squared theta, well, first you got a t squared that's common on both terms here. When you square these, and then you have a cosine squared theta and sine squared theta. Those add to 1, okay? And you have the square root of t squared, which is absolute value of t, because t could have been a negative number, okay? The one they showed here appears to be positive, but it could have been back here. The t could have been back here, so it could have been negative. So this gives you the absolute value of t, okay? Whoops, one more. Absolute value of t. So you can write the slope of the secant line through these two as being this. The alpha of xy minus alpha of x0 y0 over t, slope of the secant line, because this is the change of x. Okay, they sort of snuck that in on you, but that is the change of x. Which is, this one is alpha of x0 plus t cosine theta, that's what your x was, comma y0 plus t sine theta, that's what your y was, minus alpha of x0 y0 over t. And finally, by letting t approach 0, you arrive at the following definition. This is what we've been aiming for, the definition of the directional derivative. Boy, it feels like you went around your elbow to got to your ear, right? Okay, let f be a function of two variables, x and y. Let u equal, now it's a unit vector, cosine theta I plus sine theta j. Always a unit vector, because sine squared plus cosine squared is 1. Be a unit vector. Then the directional derivative of f in the direction of that vector u, whose key angle there is theta, is noted by the directional derivative with respect to that angle, to that unit vector u of the function f is, okay, directional derivative is the limit, this limit we just had there, as t goes to 0, of f of u plus t cosine theta, alpha, comma, y plus t sine theta minus alpha of xy, provided that limit exists. If that limit exists, then you're okay. Calculating directional derivatives by this definition, similar to finding the derivative of a function of one variable by the limit process. Hopefully we're not going to do that too much. A simpler formula for finding directional derivatives involves the partial derivatives of f sub x and f sub y. Okay. And here it is. If f is a differentiable function of x and y, then the directional derivative of f in the direction of the unit vector u is equal to cosine theta I plus sine theta j. The key thing there is your angle theta. Then the directional derivative in the direction of that unit vector of that function f of xy is f sub x, the partial of f with respect to x, cosine theta, plus the partial of f with respect to y, sine theta. Oh, that really simplified it. Because if you know the function, you can calculate the partial derivatives. You know the angle, you know sine and cosine. Okay? So this is directional derivative in the direction of that unit vector u with that sine and cosine. Okay. Trying to get to a good stopping point. I guess this is as good as any because we're awfully close to time, aren't we? Okay. So we'll start with that next time. I don't know if we got enough covered. No, we didn't do enough to do anything new here. So we'll start there on page 920 next time. Just barely scratch the surface of this section. But just to review again, this is 13.6. We'll do it. It's a long section. Then we'll do 13.7, and that's a fairly long section. Then we'll do 13.8, which is a fairly long section. And I guess, I don't know, I think we'll probably have to skip 13.9 because that's just, it's a short section, but we just don't have time. And then Lagrange multiplier 13.10 we'll skip. That's it. So after we finish 13.8, I may just do a quick slideshow of 13.9 and 10 just to get you familiar with it in case you ever need it. But we won't be expected to have that on the test. All right, so we'll pick up here next time. No new homework exercises there. But let's see, where did we start today anyway? I think it was in nope. Were we at the beginning of 13.5 today? No, we're at the end of 13.4. Okay, got it. All right, good deal. Oh, I did tell you all about the good news, bad news, right? Or did I? Yeah. Okay. Yeah. The bad news is next Thursday's a holiday. The good news is it doesn't affect us any. We meet both times next week. All right. Good deal. All right. Let's